Hi friends, now we are going to discuss 6.12 is collisions. This is very important topic. This topic is always asked in examination. We study different situations. In this one, somewhere collision happens. In some case, there is no collision taking place. Whenever we see motion, there is a change in position, change in time. Certain parameters do change, but there are certain parameters which do not change at all. Momentum is one such parameter. Energy is another parameter. Therefore, they are called as basic laws of nature, law of conservation of momentum. In an isolated system, if external force is not acting, the total momentum of the system remains constant. This is the law of conservation of momentum. There is another one, law of conservation of mechanical energy. The total mechanical energy of the system, isolated system, is always constant. And both the laws valid, or these are universal laws, because universe is considered as an isolated system. Then, whenever there are non-conservative type of forces, the total mechanical energy is conserved, but all energies we have to account for. For example, when the car collide on truck, then at the time of collision there is a sound. Similarly, there is a spark, there is a drag. All these are sound, light, these are the forms of energy, and when we count it, all the energies together, energy due to conservative forces and energy due to non-conservative forces, the total energy always remains constant. So it's a universal law. Then what does changes? Let us see now. First, law of conservation of momentum, very simple thing. When two bodies collide on each other, then delta P1 is equal to F12 delta T. This is the force by 1 on second. Similar manner, there is the delta P2 F21 delta T. This is the force on second and first. But we all know, according to law of Newton's third law, they are equal and opposing. So P1 plus delta P2 is equal to F12 delta T minus F12 delta T, which becomes 0. So delta P1 plus P2 is equal to 0, or delta P is equal to 0. This holds good for all forces. This is a change in momentum, always remains constant. Similar manner, energy conservation do take place. But now we are going to consider collisions. There are three types of collisions. One we call it as the perfectly inelastic collision, inelastic collision, and then elastic collision. Let us see the difference in this one. For example, this is body of mass m1, which is moving with initial velocity v1I. It is v1I is the velocity. It's moving here. There is a body of mass m2, which is v1 v2I, which is at rest. This one is at rest. After collision, this body moves in this direction, m1 v1 f finally. This moves to this one, m2 v2 finally, and there is this angle is theta1, this angle is theta. There is a general collision. Whenever collision is taking place, this sort of things are happening. Only special case we are taking, m2 is at rest. By this one, generality is not lost. We can consider it as a moving also, but here we are taking it at rest. Now, first one. What is the first case? It is perfectly inelastic collision. What is the one? Perfectly inelastic. two bodies stick together and move with the same velocity, it means that they are moving with same velocity after collision. It is known as a perfectly inelastic collision. What is happening now? This is M1. And then after this one, both of them move with same velocity. They stick and they move with the same velocity. In this one, deformation is not relieved at all. Whatever deformation is taking place, it is not relieved at all. It means that this V1F and V2F is equal. Both of them are equal and they move with the same velocity. Now let's see law of conservation of momentum. First one, P initial is equal to P final. M1 V1I plus M2 V2I, which is equal to M1 V1F plus M2 V2F. What happened? This is 0. So V2I is equal to 0. In case of perfectly inelastic collision, V1F is equal to V2F. So M1 V1I is equal to M1 V1F plus M2 V1F. So M1 V1I is equal to M1 plus M2 V1F. We take it V1F is equal to M1 plus M2 V1I. Vf or final velocity of both, it is equal to M1 plus M2 V1I. Now this is final velocity of this one in case of inelastic collision. Now what is the loss of kinetic energy? Let us see. What is a loss of kinetic energy? What happens here initially? Initial kinetic energy is equal to half M1 V1I bracket square. Final kinetic energy is half. They stick together. M1 plus M2 and then V1F square. This is final kinetic energy. Now let's find change. What is the change in kinetic energy or loss of kinetic energy? Next one. Loss of kinetic energy is equal to K initial minus K final half M1 V1I square minus half M1 M2 V1F square. I can substitute M1 V1I square half M1 plus M2. V1F is equal to, here it is coming as V1F is equal to M1 plus M2. It's a minus will come here. V1 bracket square V1I bracket square. It's a square here. So next one, it is equal to half M1 V1I square minus this one will get cancelled here. It is minus half. It is M1 plus M2, M1 plus M2 bracket square, M1 square, V1I bracket square. One is cancelled. So now there remains common. I am taking half M1 V1I bracket square, 1 minus M1 plus M2, which is equal to half M1 V1I square, M1 plus M2 minus M1, M1 plus M2, cancel it, which becomes half M1, M2, M1 plus M2, V1I bracket square. This is loss of kinetic energy in case of elastic collision. This is coming as loss of kinetic energy in case of elastic collision. Perfectly inelastic collision. This one is for perfectly inelastic collision. Inelastic. Now let's see what is the meaning of elastic. Before that, this one is perfectly inelastic. What is inelastic? Inelastic collision. Inelastic means when there is momentum conserved but kinetic energy is not conserved. See, I am talking about kinetic energy. Here, momentum and total energy is conserved, but kinetic energy, initial kinetic energy and final kinetic energy is not same. Such type of things we call it as inelastic collision. We cannot derive any particular derivation for this one, or we cannot do any detailed calculations of inelastic collisions because lot of non-conservative forces are involved. But in case of elastic collision, this is perfectly inelastic. This is inelastic, but perfectly elastic, or it is also called as only elastic. So now we are going to discuss that is elastic collision, or which is also known as perfectly elastic collision. What is the thing there in perfectly elastic collision? In this one, momentum is conserved, total energy is also conserved, at the same time kinetic energy is also conserved. Let's see. Now we are taking special case. This one. This we have taken M1 here, M2 here, that is theta 1 and theta 2. But we are taking theta 1 is equal to theta 2, which is equal to 0. It means that they travel in straight line after collision. It's a special case we are considering. Now first, law of conservation of momentum. That is M1 V1I, which is equal to M1 V1F plus M2 V2F. From this one I get it M1 V1I minus M1 V1F M2 V2F. M1 is common. V1I minus V1F, which is equal to M2 V2F. This is equation 1 and marking. From law of conservation of kinetic energy we get half M1 V1I square, which is equal to half M1 V1F square plus half M2 V2F square. This is all half, we cancel it. So M1 V1I square is equal to M1 minus here V1F square, which is equal to M2 V2F square. M1 is common. V1I square minus V1F square, which is equal to M2 V2F, which is equal to V1I minus V1F, V1I plus V1F, which is equal to M2 V2F. This is equation number 2. If I divide this by 1, if I take it M1 V1I minus, which is equal to M2 V2F, M2 V2F. is also cancelled. This is cancelled. So V2F is equal to, we get it as V2F is equal to V1I plus V1F. V2F is equal to, we get it as M2 square. It should be square. This one is square. This is square. So one is cancelled. We get it. V2F is equal to V1I plus V1F. This is derivative. V2F is equal to V1I plus V1F. Now from this one, we can substitute it back here. Just put it back here. So we get it. Let us see. M1 V1I minus M1 V1F, which is equal to M2 V1I plus, I substituted it here. Open the bracket. M1 V1I minus M1 V1F M2 V1I again plus M2 V1F. Just V1I we can take it to one side. V1I to this side. M1 V1I minus M2 V2I, which is equal to V1F plus M2 V1F. So M1 minus M2 V1I is equal to M1 plus M2 V1F. So V1F is equal to M1 minus M2 M1 plus M2 V1. So this is expression for final velocity of first particle in terms of masses of two particles and initial velocity of first particle. See, these all things are initial. Now let us find out M2F. How to get it? M2F. Where is, or not M2F, V2F. That is V2F is equal to V1F plus V1I. So V1F we can put it here. M1 minus M2 divided by M1 plus M2 V1I plus V1I. Take it common. We can take V1I common. 1 plus M1 plus M2. M1, this is minus M2. Bracket common. Except simplify this one. Just it is V1I is equal to V1I. LCM is M1 plus M2. Take it. It's coming M1 plus M2 minus plus again here. M1 minus M2, which is equal to V2F. So these are cancelled. 2 M1, M1 plus M2, V1I, V2F is equal. So this is the final velocity of second particle. There are two velocities: initial velocity of final velocity of first particle and final velocity of second particle. Now from this one we can say two cases. One is if M1 is equal to M2, then what is going to happen? Let us check it here. That is V1F is equal to 0. Then V2F. What will happen to V2F? V2F is equal to V1I. So there is exchange. Initially, second particle was at rest. First was moving with this velocity. In case of this one, when masses are equal, then the second particle starts moving with the velocity of first particle, and first particle comes to rest. And it is a very common experience in marble when the children plays marble or in caramel stone. When we strike one bit with another one, if their masses are equal, one start moving, other comes to rest. In such case, the velocity acquired by first one or velocity acquired by second one is same as that of the velocity of the first, but first come to the rest. That's all. Remaining problems we will discuss it in next video. Thank you.